Okay, so I think we're all set, so we can start this Friday's seminar. So today we are very pleased to have Joe LaCasce here with us. So before starting, I would like to welcome you all. Well, we have a lot of people in here in the audience, so we're very happy. And then we also have some people joining on live on YouTube, on Facebook, and also on Zoom. So hopefully there is a lot of people joining in. And well, as you know, we will have the seminar, and then as usual, we will have a Q&A session. So we're gonna start with questions here from students, from everyone else here in the room. And then we'll move on to, we'll open up the mics for people who is online so that they can also ask some questions. Before starting, I would like to personally and sincerely thank Joe for being here today. I met Joe a few months ago at a seminar, well, a conference in Brest, in Plouzané in France. And as soon as I invited him over, I think he was very enthusiastic and almost saying yes immediately. So we are very, very happy about that. Joe has been collaborating with some people here in the department previously, and he continues to collaborate with people in here. And we hope that those collaborations continue in the future. Let me just briefly mention some of his outstanding CV. It's going to be a very brief one because even though Joe has a very large career in oceanography and meteorology. And so currently he is a professor of oceanography and meteorology at the University of Oslo. He is a guest researcher at the Woods Hole Oceanographic Institution too. He has a PhD in physical oceanography from the MIT Woods Hole Joint Program and was a postdoc at Ifremer in Brest, France. He was an assistant scientist at Woods Hole from 1998 to 2002 before moving to Norway, where he currently lives. He studies turbulent transport and how to measure and interpret Lagrangian statistics. He also studies the dynamics of large-scale currents and waves and how both are influenced by bathymetry. Most recently, he has been working on climate change, in particular on the dynamics of the Atlantic meridional overturning circulation and of meridional heat transport in the atmosphere and ocean. And I think that's a bit of what he's going to be talking about today. He was an editor at the Journal of Physical Oceanography and has published over 90 scientific articles. So without further ado, thank you so much, Joe.
Okay,
take it away.
Yeah, great. Okay, great. It's great to be back. I was here 7 years ago, and I really enjoyed being here. It's a wonderful, wonderful place. So I was happy to be back. It's like she said, when she invited me, I said, I would love to come. I would absolutely love to. So this is interest. It's a little different than what I normally work on. And normally I talk about turbulence, and we have lots of equations, like what we're writing behind here. This one, I think there's one equation, maybe two, that we snuck in a second. There's almost no equation, but it's on a topic which it's been quite a bit in the media lately. So you probably heard these stories about how the Gulf Stream is shutting down, right? There's a group of people that keep saying the Gulf Stream is shutting down. So the question is it? Is it actually shutting down, and will it get weaker in the future? Okay, so this is the things that we're talking about. And there's something here in particular that you may or may not know about, which is something that's an unusual name. It's called the North Atlantic Warming Pole. Okay, I'll explain what that means. So somebody was saying to me 2 days ago, why is it warming pole? It sounds like you have a region which is heating up, and this is the opposite. So it's actually cold. But I'll explain what that all means. This is some work that I did with the former PhD student who's now in England, Orof Madan, and also with a former PhD student who's now a professor in Oslo, Ada Yermans. So they did a lot of these calculations. Okay, so this is what I'm talking about. This is some example from different media sources and reputable ones as well. So this is, for example, this is The Economist over here, and they're saying the shutdown of ocean currents could freeze Europe. Okay, this one down here, I don't know how good your Norwegian is, but in case it's not great, I'll translate for you. It says they're concerned that temperatures could go down to -50 Celsius if the ocean current system collapses. Okay, there are people that are having this discussion now in Norway saying, why are we worried about global warming? You know, we're going to be freezing, right? Because the Gulf Stream is going to collapse. Then you have the Guardian here saying, we don't know where the tipping point is, climate expert on potential collapse of the Atlantic circulation, and so forth. So there's a lot of this that's out in the news. And what you end up with in the public is this, right? So there was an article that said, you remember the day after tomorrow, this film? And they said, an expert has predicted it could come true, all right? So suddenly you have this idea that the Statue of Liberty in New York is going to be up to her chin in ice, right? Because the Gulf Stream is going to shut down and we're going to have this, right? So is that really true? People come up and ask me this. I was interviewed by a journalist this week in Norway saying, is this really going to happen? Not exactly. Okay, so I'm going to explain. All right. So what we're talking about here is the Atlantic Meridional Overturning circulation. And it's actually part of a global overturning, right? So it's a system of currents that are all connected. And it's one of the reasons I'm so fascinated by this, because it really is global, right? It's a global circulation system. So you have flow here flow in the North Atlantic. You have these deep boundary currents that go down into the Southern Ocean. They get into the Southern Ocean and then they circulate around Antarctica. And then some peel off in ways that we're not really certain about. They're peeling off, go into the Pacific, go into the Indian Ocean, some back into the South Atlantic, and then upwell. And we don't really know that either. This is actually a really fascinating question, how those deep waters get back to the surface. So, for a long time, they thought this happened in the interior, but I think a lot of us believe now it's happening on the boundaries. But anyway, it comes up, and then it eventually circulates back to the North Atlantic. So it comes back in the Atlantic, and then part of this, and then it gets denser and denser, and then it sinks, and then it makes a big loop. Okay. Again, this is a very simple schematic. There's a lot here that it's much more complicated than this, right? It's not, for one, it's not laminar ribbons of flow, it's eddies all over the place. But that's our general thing. And why is it called AMOC? So why do people call it AMOC? Because if you're in the Northern Hemisphere, right, then we have this Northern Hemisphere bias. And you see that the only thing that's going on here is in the Atlantic, right? So it's in the Pacific, there's really not much going on at all. And of course you have land over in the Indian Ocean. But I think, you know, we should really be calling it just the Meridional Overturning. Drop the Atlantic, because it is a global system. All right. So when people talk about AMOC, okay, this is one of my equations, but this is what they do for a lot of climate modelers. This is the ocean circulation. Whoops, is this cell. So what they're doing is they're taking the velocities here, like over here. This is the north-south velocity. This is the vertical velocity, and you integrate it. This comes from the continuity equation. So you integrate it. This is an exact result, and then you can define a stream function. So you take this complicated three-dimensional circulation and you turn it into a two-dimensional overturning, okay, which is convenient, right? But it's also a little misleading because, you know, here we have things happening on boundaries and things happening in the interior, very complicated mess. And here it just looks like we have a nice smooth overturn, something like the Hadley circulation in the atmosphere, right? So something that's But this is what we use. It's a standard output variable in a lot of these climate simulations. Okay, so here's an example of one. This is a case that I'm going to be talking quite a bit about, is what happens when you do something really drastic, you quadruple CO2 in the atmosphere. So the models that are used for the IPCC reports, they're run in all these different countries, right? But they have some standard runs that they use. And one of these standard runs is the quadruple CO2. So you turn on day zero, you go whoop, like this, and you increase CO2 up to 4 times its initial value. And then you look and see how it changes. It's a terrible climate. If this happened, we would really not be very happy. But what it's great for is trying to understand how the ocean and atmosphere react to that type of forcing. So up here on this one here it is. That's what it looks like before you turn on the forcing. all right? And this is the global ocean. You know, you've integrated over the whole ocean. So we don't know where the Pacific is anymore. We don't know anything. We just have this overturning circulation. And this red is a clockwise flow. So it's going north. That's happening in the Atlantic. And then it descends, and then it returns at depth. So that's our overturning circulation. That's this AMOC cell. We have some other ones here as well, which I'm not going to talk about. This is the Antarctic bottom water cell. And then also this little feature up here in the Southern Ocean is called the Deacon cell. Okay, but we're going to focus mostly on this one in the north. When you quadruple CO2, you wait about 100, 150 years. It looks like this. So this one over here is what happens. That cell is really weakened. Okay, so this AMOC cell, this overturning cell, has gotten much weaker. And if you take the difference of these two, it looks like this one here. So that blue blob now is the change in AMOC, and you can see it's much, much weaker. Okay, so this is what people are really interested in. And when they talk about, you know, when they talk about the overturning shutting down, AMOC shutting down, this is what they're referring to. Okay. Now, before we get carried away with models, it's useful to actually ask this question: do we have indications that it is weakening, that it is slowing down, right? There have been some articles which have been published which said, yes, this appears to be true. So there was a paper that was written back in 2014 where they were looking at current meter data in the North Atlantic, and they were saying, yes, oops, it looks like all of a sudden there was this precipitous drop, about 30% weakening in the transport going through, all right? And this then was also, there was another paper that came out in 2014 and said, yes, this is part of a trend. Well, the problem is, and this is an example, this is from the Florida Straits, the problem is that what you can see is there's a lot of year-to-year variability. So it just happened that at that time, there was a 30% decrease. They waited a couple of years and actually came back again. All right, so this was not actually, was not a major weakening. It was just a blip, a fluctuation. This is an example. The one here is from some measurements from a cable. There's a cable that runs across the bottom in the Florida Straits, and they were able to use that to infer the currents. And so in this paper, it said that there's a statistically significant decrease in the transport that's going through. Okay, but there's other studies. So involving these current meter arrays. This is called the rapid array. So this is a joint American European deployment, I think. I don't know, a lot of people involved with this. And with current meters across at 25 north, there's another one down here in the Caribbean, which is called the MOVE array. There's another one which is further up north near Greenland, which is called the OSNAP array. And so they're taking these measurements at all these locations and looking at the transport. And in all cases, they have not detected any significant trend. Okay, now, these are not long time series. These are typically at best about 20 years, which is really short for a climate time series. But the point is, we haven't really seen it. And there was another paper which came out recently where they revisited the calculation from this cable across the Florida Straits. And they made corrections because the measurement depends on changes in the magnetic field, the Earth's magnetic field. And they made those corrections, the trend went away. So we really don't have any observations now that say that AMOC is getting weaker. Okay, but where we do see it is in models. So these are a number of different models run with different climate scenarios. So not just quadrupling of CO2, but different less dramatic CO2. So SSP 119 is a different scenario, 126. The strongest one is this 585. And in most of these cases, the overturning circulation weakens in the next 100 years. So from 2000 to 2100, there is a general weakening that's happening. So that's when we're really seeing this, is in models in the future. So this will be a theme that we'll keep coming back to. Is that also realistic? Are the models getting it right? Okay. Anyway, so the first thing I want to do is I'm going to tell you about the first paper that we wrote about this, which came out last year, where we looked at some of these model runs under this drastic forcing, quadrupling of CO2, and we're going to look and see why is it weakening. We're trying to understand Does it weaken? Yes, it does. You'll see. But why is it weakening? So we're going to look at relation to various different forcings. So this is a picture, a time series of the maximum of that overturning cell as a function of time. So the axis here goes from 0 to 150 years. So this is over the 150-year period. That's a typical period for doing this test case. We've normalized this to be 1. So in all cases, it's the same strength initially, and then it falls. So you can see that the overturning is weakening in basically all of these simulations. Now, some cases, it's really dramatic. It's down to about 0.2, so that's an 80% weakening of the overturning. But in other cases, it's much less. It's only, say, about 10 to 15%. So we have a continuum of responses. Sometimes people will talk about the overturning as a bistable state. So let's say it's on or it's off. Right? So you either have it on or off. But what we see is that the models have a whole range of different behaviors. Right? So that's one thing. The second thing is that the models don't agree. Okay? So there's something going on in these models which is not the same. Right? So we have a different reaction in all these cases. Okay. When you look on average, this black line, that's the average of all those curves, it's about a 55% weakening. So if you quadruple CO2, it's going to decrease by 55%. And our Norwegian model, which is the one I just showed you, it's this orange curve, it weakens a little more. So this it's on the strong side when it comes to reactions. The other thing that is interesting here is that it is the time scale. What I'm used to thinking about is that the ocean has very long time scales, right? So we think, you know, you go to a new climate state, and it takes 1,000 years to adjust to that state. Well, here we see that this AMOC is happening rapidly. We're in a new state already by 60 years. And the E-folding time here is about 20 years. So it's actually fairly rapid. Once it starts to weaken in this dramatic scenario, it happens pretty quickly. Okay, so then we checked to see what's causing this. What are the different forces? So one of the first things we looked at were the winds. So one of the things you often hear is that people say it's a wind-driven overturning. The overturning is responding to winds. So we looked at the changes in the winds over the subpolar gyre, in particular, over this region of the Atlantic. And what you can see, this is a typical case, I think it may be from the Norwegian model as well. You see blue regions and red regions and blue regions. Okay? And that means that it's the curl of the winds, because that's the part that's important for the wind for driving the ocean. In some regions it's strengthening, some regions it's weak. Right? So it's not a clear picture. All right, so what we did was then we averaged over the subpolar gyre and then compared it in these different models to the weakening that you get with AMOC, and you can see the results are all over the place, right? So wherever the wind stress curl changes here, it has almost no relation to AMOC. So the correlation is minus 0.2, and it's not significant. Okay, so we concluded that it's not the winds over the subpolar gyre. Okay? Maybe it's somewhere else, but it's not here. So we did check somewhere else. We also looked in the Southern Ocean. So one thing, so there's a line of thought in the overturning literature that the winds around Antarctica are very important for the overturning, because at the surface you're exporting about 20 sparedrift, so 20 times 10 to the 6 million cubic meters per second. And that's about the same as the overturning. So and in some models you see that there's a link that this goes all the way down into the Southern Ocean before it comes up. All right, so we checked that. In these runs, the winds get stronger in all cases. The winds are intensifying. So if you look at this axis, this is the zonal wind stress change, it's positive. So in all models, you're seeing stronger winds. But again, the AMOC changes all over the place. So again, we conclude it's not the winds around the Southern Ocean. It could be, again, if you wait 1,000 years, maybe you start to see some relations between this. But on these timescales, it's much too fast. So it's got to be something else. What it turns out to be is it's the density field. Okay, the density field is really changing in these runs. So this is the Norwegian Earth system model. This is the difference between the surface density at 150 years after turning on the CO2 and what it was before you turn on CO2. So you have this, the deviation that you're getting. This red up here, north, this is actually north of the separated Gulf Stream and the North Atlantic Current, that's red. So that means that the density is getting lighter. So we have lighter water that's up here, okay? In the subtropical gyre down here, what you see is that there's not really much of a consistent change. It's a little bit higher, a little lower, but not much. It's north of the Gulf Stream system that you see that you have a big change in the surface densities. Okay, well, what you can do is you can break that up into components. So you can look at the change that's due to temperature and the change that's due to salinity, right? And if you look, so the first panel here is the change due to temperature. And what you see is that in the subpolar gyre, so the subtropical gyre down in the south, the water is getting warmer. So it's getting lighter, right? So that's part of that. That warming up in the subtropics is giving you lighter water. Up in the, just south of Greenland, you've got another region here where you have, where it's getting colder. And that's what I'm going to come, that's the warming hole. I'll come back and talk about that in the second part of this talk. But this is what temperature is doing. So the temperature is actually increasing the density gradient, right? It makes it lighter where it's already light, and it makes it heavier where it's already heavy. So it's making that change. What about salinity though? Well, in the subtropical gyre down here, we it's actually getting heavier. It's blue. It looks unusual, but we plot it this way to make it look like temperature, right? So if you have more salt, it's like it's getting colder. So it makes it easier to. It takes a little while to think about it. Why blue would be saltier, but that's what it is. And so, and when you combine that with this, with the warming here, so that's making it lighter, that's making it heavier. Those two tend to cancel each other. So in the subtropical, that's why the subtropical gyre is not changing very much. Okay, but in the north here, it's getting fresher. There's fresh water that's pouring into the subtropical gyre, and therefore it's getting lighter, right? And when you combine those two, it's the fresh water that is the important force. So because the equation of state of seawater is nonlinear, you have more salinity dominates when the water is cold. When you're up in the subpolar region and north of that, salinity is having more effect on the density, and it makes it lighter. So even though it's getting, that warming hole is making it colder, what you see is that on average it's getting lighter because of the fresh water. All right. Now, if we do these correlations with the change in AMOC, now you start to see some correlations. So this is the density drop across the North Atlantic Current, so the separated Gulf Stream. So we just take the density north of that and subtract the density south. We look for this and we correlate that with the AMOC change, and it's well correlated. So it's not a huge correlation, it's 0.531, but that's partly because we have a couple of runs, 1, 2, 3, 4 runs, and I'm not going to name any names, but there's that, you know, that are not falling in it. You remove those 4, and then suddenly the correlations are over 0.8. So it is pretty strongly correlated for most of them. Just a couple of these models that aren't behaving that way. When you look at the change with regards to temperature, though, it's not. So there's no clear correlation, and it's insignificant. So the temperature changes and AMOC are not consistent. But when you look at the salinity, so the change in density due to salinity, again, you have a very strong correlation. So this says that the change in the freshwater content across the North Atlantic Current is consistent with this change in AMOC. If you have a bigger change in density, then you have a more weakening of AMOC. Okay. And this is, it's actually really interesting to watch this because it happens fast, right? So here, top row is density. This is surface density. Middle row is surface current. The bottom is the overturning stream function, the change in overturning. So this is the change in all these quantities. This is, the first one is year 1 to 5, okay? See this tongue that's coming off of North America here. This is a tongue of lighter water, which is actually fresher water, which is coming out from the North America, from off the coast of North America into the subpolar gyre. In year 6 to 10, you can see how it gets stronger. We have more of this stuff coming in, so there's more of a change in the density, and it continues to intensify all also already by 10 years, right? You have this strong signal of fresh water entering into the subpolar gyre. Now, at the same time, what you see here is if you look at the currents in the North Atlantic current here are weakening at exactly the same time. All right. Now, this isn't a big surprise if you know about thermal wind. So what thermal wind is, it says that if you have a change in the density gradient, you get a change in the velocity shear. Okay? So as you are changing the velocity difference across this system, across the North Atlantic current Gulf Stream, you're actually weakening it at the same time. And you can see this too. So year 6 to 10, 11 to 15, and 16 to 20, it's getting weaker and weaker. So by 16 to 20, the whole system appears to even back down along the coast here. It's that whole current system is getting weak. It's collapsing. Now compare this to what's going on in the stream function. You can see at 6 to 10 here, all of a sudden you're starting to see a weakening, overturning. And where is that happening? It's happening at 40 north. 40 north is where the current here is separating from North America. Okay. So AMOC is weakening exactly there first. Now AMOC, if you remember the AMOC stream function, all it is, that's the velocity field, right? You're just integrating the velocity field to get a stream function, right? So if you change the velocity field, you change the stream function. That's all we're seeing here is that as that Gulf Stream North Atlantic current is dying out, then the overturning is weakening at the same time. So by 16 to 20, already you have this big blue blob of a weakened AMOC. And it's because that current system is actually weak. All right. Now, where is this fresh water coming from? So it's coming primarily from two sources. One is sea ice. That's really the big one. So the sea ice in these simulations, you quadruple CO2, the Arctic heats up immediately, right? It's unbelievable how fast this happens. Within a year, the Arctic is cooking. And so the sea ice melts away within the first couple of years in these simulations, all gone. So the permanent ice is gone. You can form ice in the wintertime, not so much, there's no ice in the summer. All that fresh water then pours down, runs down along the western boundary, and then that's the thing that's coming in as a ton of fresh water off of North America. Yeah. So when you look at these different contributions, then there's this from sea ice. There's also a contribution from runoff. Runoff is increasing because you have more precipitation on the land, and that's all feeding in as well. And you combine these things. That's this black curve. No, sorry, it's the red curve here. That's the freshwater flux, and you can see it declining over the same period, first 20 years. That AMOC is also declining. So those two things go together. So they're going in tandem. And so that's what we think is happening. So the fresh water then from the melting ice, from the runoff, goes into the subpolar gyre, enters just north of the Gulf Stream, and is weakening that system. Okay, so why are people saying then that it's collapsing? Okay, and how are they, what is that based on? Well, these are two studies that were done. One was done in 2021, one was done in 2023, both were published in Nature. So they were high visibility, and that's why they end up in media, right? Because the media is looking at Nature all the time, and then whoop, they take it right out. Okay, what are these studies based on? Well, these are what they do. Both of these studies use different measurements from the ocean, use those as proxies, and then compare it to a very simplified model like this. Okay, that's a first order ordinary differential equation with a noise term. Okay, so there's a noise. So that's a simple stochastic first order equation. That's the model, that's the test model that they're using. One of the proxies that they use is temperature in the subpolar gyre. Not density, but temperature in the subpolar gyre. And the claim was that because that is getting colder, I'll come back to this, why that's getting colder, that's a signature that AMOC is weak. So that was one conclusion from this paper. Basically the same conclusion in this paper that came out a couple of years later, a little more complicated model here, down here, but still a first order equation. And then you have, and it's temperature from this region that they're using. So they're looking at the subpolar gyre. They're saying, oh, what's the temperature doing? And then they're saying, oh, okay, it's getting colder, AMOC is dying. All right. So what is that region? Okay, this is the warming hole. All right. If you Google warming hole, then you can end up at Wikipedia, and there's something in Wikipedia. It's not called the warming hole; it's called the cold blob. Okay, so there's a page there saying the cold blob, and so in the Wikipedia page it says the cold blob in the North Atlantic, also called the North Atlantic warming hole, describes cold temperature anomaly of ocean surface waters affecting the Atlantic Meridional overturning circulation, which is part of the thermohaline circulation, possibly related to global warming-induced melting of the Greenland ice sheet. Okay, a lot of interesting stuff in there too, right? Okay, is this all going to? The great thing about Wikipedia is that it's always it's always in motion, right? Because as we know more, then you can go in and you can edit it and do that. So I'm guessing in 10 years it's going to be different, but anyway, that's the current understanding. And this is. But the thing about, so the thing about it is that why do they call it a warming hole? It's because it's in the residual field. I'll show you this in a minute, but it's what happens if you take the temperatures now, right? And then you subtract what the average temperature was from 1950, say, to 1980. That's what this picture is, right? And that's where it shows up. So it's not actually a cold region. It's not if you went sailing out there that you would say, ooh, it's cold, ooh, right? No, it's only if you go sailing across and you say, oh, it's nice and warm, but it's not as warm as it ought to be, right? It's warming less than it is. And that's why they call it a warming hole. Okay. Now, is it here in the observations? Well, these are reanalysis products. So it's not quite the same as observations, but it's our best guess. So we take observations, we take a model, we put them together, and we do this. There's different versions of this. This is from the UK Met Office, this one up here, and then 3 other products over here as well. And in all these cases, it does show up. Okay, so when you look at the temperature, the average temperature from 2010 to 2020, and then you subtract the mean temperature from 1950 to 1980, this is what it shows up. And there it is in all these cases, this blue region south of Greenland, where you have anomalously less warming than you have outside. You see around it, you have here, there's quite a lot of warming along the coast, here too, and a lot of warming all around it. Right? But in that localized region, for some reason, it's getting colder. Right? Now, why? Okay, what's causing the warming hole? Oceanographers, we're human, so we like to argue too, right? And so there's been a lot of debate about what is causing this. The most common explanation for this is that it's related to heat transport in the overturning circulation. So they're saying the heat transport is decreasing, and therefore you don't have as much heat coming in, and that's what's causing this cold hole, okay, this relative cold hole. So there's a bunch of papers about that. Now, in the last couple of years, though, there have been some more papers coming out saying, well, no, you know what? We can do this in the atmosphere only. You don't need to have an active ocean, right? As an oceanographer, we hate that, right? Like, what do you mean? But some of these meteorologists say, oh, you don't need the ocean, right? And so I'll show you that in a second. But there's other causes too. Some people said there's freshwater changes in Labrador Sea, Arctic sea ice melt, yes. Increased heat export. There's even been a connection to the Indian Ocean. So there's a paper that said changes in the Indian Ocean were being communicated via teleconnections to cause this. So a lot of different ideas floating around out there. Okay, here's the first one. So what you can do is they use this as a proxy. So you can take the temperature in the warming hole, you can average that, and then you look at that and then use that, and you sort of scale that, and then that tells you how the AMOC is changing. So this is a paper from 2015 where they did this. And also with models. So this is from 1850 to 2100. And you look at how the actual AMOC is varying, and then you look at this proxy based on SST, and the two of them are in sync. Okay, so it looks very much like these two things are together. Okay. Now we have to be careful, right? Because this means that they're correlated. Doesn't mean that one is causing the other. So that'll come back to that. So correlation doesn't mean causation. And these are some other studies where they've made similar claims. But that's the main. Most people would think that that's the case. But here come the atmosphere people, and what they did was they took a slab ocean, so an ocean that say is about 50 meters thick. It has no currents, right? It's just acting like a mixed layer. So the temperature can change, but there's no currents. You can specify heat transport in this layer, so you can impose a heat transport, but you know it's not part of the solution. It's just a sponge basically at the top. And under these conditions, they perturbed the atmosphere, and they said, oh look, you know we can get cooling here south of Greenland, just like there. And this study said the same thing. So they're saying, yeah, you know, the atmospheric cooling can give you this forcing too. We're going to check all of these. Okay, so that's the no ocean case. All right, so here's what we did. All right, we're going to look at the warming hole. We kept seeing it, right? It was there. And we kept thinking, we got to go back and look at this warming hole. Eventually, we have to do that. And so then we did. Okay. We're going to look at this. We're not going to do the 4 times CO2 case. We're going to look at this SSP 585. This is basically what happens if we just ignore climate change. We have a neighbor to the north here who doesn't really think that climate change is happening, and so then you just increase CO2 as you will, and so it just goes like this. That run, by the way. So here's the 1980 level of CO2. This is this purple run here, the SSP 585 run. You will quadruple CO2 in about, I think it's about 120. So you see that it actually gets up here too. So we're going to get there to quadruple CO2. All right, but it's a strong scenario, but it's supposed to be more realistic. All right, we're going to look for what's happening in this. We're going to start with a Norwegian Earth system model, and that's our favorite model. Right? And so we're going to pick that one apart, and then we'll go back and see if the other models are doing the same thing. All right, so this is what I'm talking about the sailing. On the left is the reference. Those are the sea surface temperatures between 1950, that's the average from 1950 to 1980, all right? And what you see is, so the colors here, this is warmer down here, north of the North Atlantic currents, colder over here, colder up here, and as the North Atlantic current turns up into the subpolar gyre, you see that you've got this warming that's over here. So these are warmer temperatures over here. Now, what does it look like from 2005 to 2014? It looks like this, right? So you look at that and you say, well, that hasn't changed very much, right? And if you were sailing out there, exactly, you would not notice any difference, right? You have to subtract them. So if you subtract them, you get this one over here on the right, right? And that's when it shows up. Okay, so that's the warming hole. So it's anomalously weak. Now it's only come in the last, it's roughly in the last 20 years or so. So it's something that started since about 2000, maybe even later. So 2005, 2010. Now, so it's something that's happening right now, which is kind of interesting at the same time. Like what is going on? If you go back to 1990, you don't really see much of an anomaly. In 2000, look, you had a big warm anomaly over here, and you start to see some cold anomaly coming off here, okay, in this range. But then it intensifies over here in the center of the subpolar gyre, south of Iceland, in that area there. And then suddenly there's this big anomaly that's showing up. But I want to just point out a couple of things, and we'll come back. One is that, look over in the Labrador Sea, it's also cold. Okay? So that's anomalously cold as well. So there's something happening south of Greenland, which is also cold. And if you look down here, that's actually quite warm. So you have warming down here, you have warming up there. Right? So we'll come back to that. All right. Now, the beauty of these models, okay, models have their issues, right? But the beauty is we can ask, how are things going to change at 2100? How is it going to look when you go further out? So this is 2040 on the left, 2060 to 2070, and this is 2090 to 2100. And what you see is that cold anomaly is going to intensify, right? So it's here it is, and there, and there. It's getting more and more anomalously cold. Of course, it's still warm, but it's less warm than not. But you also see here at the same time, look at this, coming off of North America, this is anomalously warm, and that's getting more, and that's also getting more. Right? So we have a region, the cold anomaly is really very localized. You know, to the south, it's actually getting warmer. Right. Also, and that cold persists over here south of Greenland too. So we have that happening at the same time. Okay. So the first thing we want to do is the atmosphere responsible for this? Okay, let's ask that question. Does the ocean matter? Right? Find out. All right. So on the left are the heat fluxes from the ocean, the atmosphere, in that period, 1951 to 1980. And I think I may have said that wrong. I think it's actually atmosphere to ocean. What's happening is it's warm. So you have warm ocean waters, and it's cooling to the atmosphere, right? So it's negative here. So it's a negative heat loss. That means that it's negative from the ocean side. We're looking at this from an ocean perspective. So negative means that it's cooling. Okay? Now in 2005 to 2014, it's also negative. It's also cooling. Okay, great. So it's a consistent picture, and it's hard to see the difference, again, between these two. What you need to do is subtract them. So here is 1990 to 2000, 2000, 2005, and now 2005 to 2015. Okay, and down here for comparison are the SSTs. All right, so here, this is the blue region here. That's cooling from in the 1990 period. But all of a sudden, it starts to turn red over here. And it's red exactly where the SSTs are blue. Okay. Whereas over in this region, where you have blue, okay, where it's cooling the ocean is red, right? So these things are anti-correlated. Actually, they're strongly anti-correlated, these two fields. And when you get over here, look at this. So here is the warming hole. That's that blue region. And the heat flux is red. Okay. Now, what does that mean? It gets tricky because we're talking about residual fields. We're talking about differences in SST and differences in heat flux. Okay. Red does not mean, so you would normally interpret the red as being the atmosphere ocean warming the ocean. That's not actually happening. The atmosphere is cooling the ocean. But it's cooling it less there than it did. So in relative terms, the atmosphere is warming. So it gets a little confusing, but where it's blue here, it's actually the atmosphere is pouring heat into the ocean. So it's the wrong sign. If the atmosphere were cooling that, we would expect to see that should be blue in the atmosphere. They should be positively correlated. They're negatively correlated. They're not doing that. Now, if you look on the other sides here too, this is also going to come back and be important. Over to the west and to the east, it's warm, so it's anomalously warm. And look at the heat fluxes. They're blue, right? So where the ocean is actually warmer, then you do have more cooling going on. So it looks like the atmosphere is just responding to the ocean. The ocean is heating up, the atmosphere takes up the heat, right? Cooling off, it's not. All right. And you look in the future, and this becomes even clearer. So 2100 is a bad time to be around models, right? Because the climate's terrible. But then everything becomes really clear, right? So then you have these clear pictures of what's going on. There's your warming hole. Also, here's this, let's call that a warming, what do you want to call that? A cooling hole? I don't know. But this region down here, you have this intense warming. And look up here, that's the atmosphere trying to warm up the ocean. And here it is trying to cool it off. Okay? So the atmosphere is just reacting to what the ocean is already doing. Well, okay. I said there weren't many equations. Well, I'm not entirely honest about that. Here's a couple. But these are the fluxes in the model. So we have two, sensible heat and latent heat. So latent heat coming from humidity, sensible heat coming from temperature. And if you look at the sensible heat, this is just written this way. That's the temperature of the surface of the ocean minus the temperature up in the atmosphere. Okay, at a reference height. So usually 10 to 20 meters. All right, the atmosphere is colder than the ocean. So this is usually a positive difference, and that means you have sensible heat fluxes going up. If you cool the surface of the ocean, you decrease the heat fluxes. Okay, that's all that's going on here, right? That's why these things are anti-correlated. It's just you change the temperature of the ocean, and then you change the sensible heat fluxes. It turns out the latent heat fluxes are also responding in the same way. So the conclusion is the air-sea heat fluxes are not solely responsible for the warming. They're actually working against it. And what I could show you is, if you're interested, is that over a long period of time, if you run this out to about 500 years, the warming hole goes away. And it's because the atmosphere actually warms it up. So it's actually erasing the warming. Oh, here it is. Oh, I did have it. Okay. So if you wait long enough, that's this red curve here. These are the SSTs in the warming hole. You see they fall initially over the first 50 years, but then they gradually recover. So you wait, if you are willing to wait, to 2400 or 500, whatever that is, then there won't be a warming hole to worry about anymore. So it'll all be gone, right? The atmosphere will just get rid of it. Okay. All right, so that was the first thing. So we said, no, it's not the atmosphere by itself. What about heat transport? What about AMOC? So this is this model simulation, and now we've patched together different parts of the run, so we go all the way back to 1600. Okay, that's when my great grandfather moved from France to Canada. Okay, he relocated around that time. Right, he moved there, got a farm, started doing it. So that was 1600. Okay, you look at these two things. The other one is the SST in the warming hole. Okay, this is the SST anomaly, and these two things are well correlated with each other. So you can see, even over these periods of time, they go up and down and up and down. There's a gradual increase up to about 2000. And then after 2000, everything goes poof. Okay, everything goes poof. So, and they decline together. So, yeah, okay, these two things are correlated. Right? But is this a causal relation? Okay, is AMOC causing the warming hole? All right, so let's take a look. Oh yeah, no, before we do that. Question, if the heat transport in AMOC is weakening, why then, okay, and it's causing this cold anomaly here. Why is it getting warmer down here? Right? I mean, that's part of the path, right? And then look up in the Nordic Seas, it's warm up there too. Right? So that's the path of the North Atlantic current. Why is it cooling in one spot and warming in the other spots? That was not clear to us, but so why is that happening? Okay. Anyway, what we did was we looked at some other fields. In particular, remember from the first part of the talk, we found out, well, actually salinity is a really important player here. All right, what is salinity doing during all this? Top row are the SST anomalies. We've already seen these. These are the surface salinity anomalies. You don't see much in 1900, 1990, 2000, you start to see a fresh anomaly. Okay? So you're seeing fresh water coming out. So this is anomalously fresh. It's fresh north of Iceland. So in the Nordic Seas, you see this. And it's also fresh off here. And then if you compare that with this SSTs, and look, it's exactly where it's getting cold. It's also fresh. Right? And then when you get out here, here's the warming hole. Warming hole is also a fresh anomaly. Okay? So fresh water is coming at the same time. All right, now you look in the future period, so we can focus over here on the 2090 period. So there's our warming hole, really established south of Iceland, in the Icelandic basin, and it's very fresh. That whole region is very fresh, okay? There's also fresh water that's coming out of the Labrador Sea, but that's actually warm over here. Where it's here, but these two fields are very strongly correlated, exactly in that warming hole. Okay, so what is going on? All right, what you can do now is, of course, the ocean, right? The ocean, it's density, right? Density is what matters. If you're thinking about the flow field, it's density, right? The atmosphere cares about temperature. If you have cold water or warm water, that's important for the atmosphere doesn't really care about our salinity. That's your problem, right? But the ocean does, right? Salinity is a big deal. And when you combine these two things, you get density. So this is the linear equation for density. So it's an approximation, but you say rho naught and then 1 minus alpha T. So if you have warmer temperatures, you decrease the density. And if you have and beta S. So if you increase salinity, you increase the density. Look at the density for these runs. All right, here this is 1990 to 2000, 2000, 2010. This is 2005 to 2015. I think it's actually 2010 to 2020. So I think it's mislabeled here. But, where's the warming hole? Where's the warming hole? Not really easy to see it anymore, right? You've got to. It's actually getting lighter here. It's getting a little heavier over here. It's not obvious where that warming hole is. All right, now, and then look at something different. Let's look at this is something that's called spice. Okay, spice is, what you do with spice is you have the same formula, but you change the sign of the temperature contribution. All right, so now if temperature is increasing, it's increasing spice. Instead of decreasing density, it's increasing spice. So now these two things, if they're working together, will show up. So here, no spice, whoops, there's a spice, and all of a sudden, there's your warming hole. So the warming hole has a very strong signature in spice and almost nothing in density. Okay. All right, so what does that mean? Okay. Well, this is something that's well known for people, particularly people that are doing work in the mixed layer of the ocean. So it's something that's called density compensation. When you have density compensation, then water that is warm, which makes it lighter, also tends to be salty, which makes it heavier. You can see this, for instance, like in the Arabian Gulf. There are regions coming off the coast where you have these tons of very salty water, but they're warm too. And then if you look at the density, right, they disappear. So you don't have any clear signature in density. Off the coast here, you have, when you have upwelling, coastal upwelling, you have cold water that's coming off, also in filaments, but often that's also fresh. Right? So it's fresh and cold, so it doesn't have much of a signature in density. That's compensation. They use different things to measure it. So whoops, this is a paper by Rodnick and Martin, and they use something that's, how am I doing? Okay, it's something called a Turner angle, where they measure this. But basically, it's these two things balancing each other off. Okay. Again, in the future period, you have this as well. So here's the density field. Warming hole is here, not much, but spice, it shows up very clearly. Okay. So what are we seeing? Well, we're seeing that the warming hole is actually a fresh blob, and it's compensated. Right? So it's instead of just a cold blob, it's a compensated fresh blob. Right? This is what where we're coming to. Okay, I'm going to sort of jump over this. What we can do here is we can look at, so this is the worst equation here, and I don't want to get into the details, but that's in this model, this is how kinetic energy is parameterized in this surface mix layer, okay? There's winds, there's also buoyancy production. That's what happens if you have fresh water coming in, and these are eddies. So this is what the eddies are doing, and this is a whole line of research, right? So people spend a lot of time figuring out how to parameterize baroclinic eddies. All right. Basically, so here's the buoyancy forcing. The buoyancy forcing just looks like the warming hole or the fresh water. Okay, you see, there's the warming hole there. That's a buoyancy forcing in the surface mix layer, which intensifies in the future period. When you look at the eddy mixing, it's the exact opposite. Okay, so wherever you have the warming hole and you have this buoyancy production, the eddies are mixing this, aggressively mixing. These two fields are strongly anti-correlated. I can flip back and forth and you can see this. So they tend to cancel each other out. What's happening is the eddies are wiping out the density signature. That's what they're supposed to do. Right? They're killing off the density signature. But in doing so, they're making spice. All right. Now, one question that comes up is that, okay, so I've got a fresh anomaly. I've got fresh water that's coming in. Why? How does it get cold? You know, why don't I just mix away all the fresh water, right? You know, well, what happens is the fresh water streams into the subpolar gyre. It's constrained by the bathymetry, and also it's hard to change salinity, right? To do it, you need to have a lot of evaporation. Right? It's a fresh anomaly. We need to evaporate a lot to get rid of that, and you don't have much evaporation in the subpolar gyre, right? That's not happening. So what you need to do is you need to then import cold water, and the way it's doing that is, this is what I was talking about. You notice you have these anomalies. Here's the heat flux anomaly. This is the buoyancy flux. On either side of that, you've got red, which means that the atmosphere is cooling the ocean. So the atmosphere is actually helping here. It's giving you, on the sides, it's giving you cold water, and then that's being injected into the warming hole. Okay, so then this is, I think, one of the last things here. Yeah, okay. This is across all the models. Basically, we see this in all the models. So this compensation is happening. This is change in SST versus the turbulent heat fluxes, change in surface salinity, change in density, and change in spice. Look at the density. There's almost no tendency here at all, right? It's just nothing, going on. SST is, salinity is, and spice is. So when across these models, on average, the models are, the warming hole is a compensated feature. Okay. All right. Now, so last thing, is it actually happening now? Okay, so let's go back to those reanalyses and check that. So this is one of these reanalyses. This is the UK Met Office, the Hadley Center reanalysis product. There's SST in 2001 to 2010. This is 2011 to 2020. And there's your warming hole. Look at the salinity. Well, lo and behold, it's fresh. Okay, so this is happening right now, right? It's up there. It's freshening. You look at the density field, and then it goes away. Right? There's no more warming hole. Right? It's gone. You go to spice, and there it is. Okay, you have a very clear signature of spice. So apparently, this is now happening currently also out in the North Atlantic. Okay. So last quick. So we said, remember we saw this. We see the SST going in line with AMOC. Those two things are going together, right? So is it causal or not? Well, no. What's happening is, if you compare that to sea ice volume in these cases, sea ice is declining because it's all melting, and it's leading. So the fresh water here is leading by about 10 years. Okay, so you're pouring the fresh water into the system. That causes AMOC to weaken from the first part of the talk, and it also gives you a fresh anomaly, which is giving you this warming hole. Okay, so it's really, again, the fresh water that's doing all of this. Okay, anyway, so the warming hole in these CMET simulations comes from fresh water. That's what seems to be going into the subpolar gyre. And it's primarily coming out of the Labrador Sea and also later on the Nordic Seas. That comes later, 20, 30 years later. The cooling by this turbulent fluxes in the mixed layer reduces the density gradients by cooling the fresh water. So we're wiping out the density signature of this. The atmosphere does play a role. Okay, it's giving you cooling on the flanks, which gives you this source of cold water. But it's not the main reason. You could not do this without the ocean. The ocean is really leading in this. And the fresh blob is constrained by bathymetry, so that's why it's so localized. It flows into the Icelandic basin. You've got steep topography on either side. That's why it doesn't spread out, right? Why is that warming hole so localized? But because the ocean is respecting the bottom. The bathymetry is so important, and so it constrains that to do that. Okay, which means that the warming hole is really, okay, sorry, meteorology, but this is an ocean phenomenon, okay? It's caused by ice. This is what we've come to realize. Ice is melting sea ice is a big deal, okay? But that gives you this fresh water, and then it's just ejected in the ocean. So the atmosphere is responding to the temperatures in the ocean, but it is fundamentally coming from the ocean. It doesn't directly reflect decrease. It's not coming from heat transport in the overturning circulation. But both of those things are responding to the fresh water. Okay. We had a reviewer who wasn't very happy about this paper. We've had a lot of trouble with reviewers on this paper. As you can imagine, there's pushback. But one of the reviewers said, "Well, can I still use this as a proxy?" Well, the answer is yes, you can. You can use it as a proxy because it is in the models. It's reflecting how AMOC is weakening, but it's not the cause, right? It's just they're responding in the same way. Okay. And in that long run that I showed you, you wait 500 years, the warming hole goes away, but the salinity anomaly stays. So the salinity really stays because it's effective, right? It's hard to change. Once you've got all this fresh water in the subpolar gyre, it's hard to get rid of. All right. I asked ChatGPT, I said, can you draw a fresh blob for me? And so the first one was terrible, but then there's this one, which I thought was kind of great, So this is the oceanic fresh blob in the North Atlantic Ocean. Thank you.
Thank you very much, Joe. So we're going to start with questions here. So if I see a student's hands raised, we're going to start over there. Paco. Okay.
Hi, thank you. I just have one question. Maybe it's a concept that I didn't, that I forgot, but there was an image or a graph that says something about the AMOC index. I just wanted to know or refresh what is the AMOC index.
Yeah, okay. So you mean way back in the beginning, from that paper, that previous paper where they were talking about the AMOC? Yeah, okay. Let me see if I can find that. Through here, somewhere. Oh yeah, it's here. That one, this one?
Yes.
Yes. Okay. Really, what that is it's the SS, it's the surface temperature in the warming hole and AMOC. So that figure is showing both of those things. But what they do is they, one of them is a temperature, the other one is a volume transport. So they convert the temperature anomaly into a volume transport. So they're just using an empirical change to say, okay, if it's colder, I have less transport. If it's warmer, I have more. That's all. So it's a proxy, but it's it's not anything. It's just based on a scaling factor.
Thank you.
Yeah.
We have Manuel here. Yeah. Any other one from this side? Okay.
Hi. Thank you for your talk. A lot of things going on. I just wanted to ask you a specific detail of one of your earlier slides, where you show the currents at different times in of the run.
Yeah.
The fresh water, which I believe it's cold, it's stemming like from the like the northeast of the United States or southeast of Canada. Is it coming down through the North Atlantic gyre, or because I believe it's
let me show you.
Okay.
Thank you. So this is one of the slides that I didn't show. This is, whoops. Oh, where'd it go? Oh yeah, okay. Oh yeah. All right, no, I have to show it here because I blanked it out in the interest of time. But this is what happens with the fresh water. Okay. These are in 2-year slices. So this is year 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. Like I said, a lot of this seems to be coming from sea ice in this simulation. A lot of it's coming from sea ice. It varies among the, there's also runoff is increasing, but the path is very similar for both of these things. The fresh water tends to come first out of the Labrador Sea. And what it does is it comes right down along the western boundary. So it's coming down as a western boundary current into the Gulf of Maine, and then it reaches the Gulf Stream, and then it goes offshore. So it begins to go offshore, right? This is year 2. You're already seeing this happening in year 2, this fresh water coming up. But you see in year 4, you see how it's really getting fresh in the Labrador Sea as you're melting, as all that sea ice is melting away and then leaving the fresh water. You also start to see it up here in the Nordic Seas. But that gives you this supply of fresh water that's then coming out. So here's that tongue at year 6. Okay, only year 6, you're seeing this tongue of fresh water coming out. And this just lengthens and intensifies and starts to fill the whole subpolar gyre. Now, the other thing is that if you look over here, this is where I was saying it comes a little bit later. Here's the Nordic Seas. You see how you have all that fresh water, but not much along the coast of Greenland. So here's year 10, year 12, year 14. Then in year 16 to 18, you start to see that that's coming out as well. So you have an additional source of fresh water coming from the Nordic Seas. So this is what appears to be happening in this case, is that you have this, where the ice is melting, it melts immediately in this simulation, 4 times CO2. And then that then flows along the western boundary and then into the subpolar gyre. Now, because it varies, so the different models, why is AMOC changing 10% in one case and 80 in another? It's because of the details of the melting, right? So sea ice is parameterized differently in these models. So that's one thing. It's also the difference in how the fresh water gets into the system. There are some cases, some of these models, where it's almost like a dam break. So you see it up in the Nordic Seas, and that water just goes, spills into the subpolar gyre from right south of Iceland. So it's coming there. Whereas other models, and I think these are probably more realistic, that it's actually coming as a western bound current and then coming in and entering that way. So, but that's basically what's happening. But there's an interesting, yeah, okay, go ahead, yeah. Yeah, well, I'm just, because you can also, you might ask a question, well, why does it, so, because the first part of the talk we're saying it's changing the density, right? And the second part of the talk we're saying it's not changing the density. Okay, so, right? So that's a funny thing, but how does that happen? All right, let me see if I can do this. Where's the density fields? So then future correlation density, okay. All right, you can see it right over here. So even in this period, this is I think 2010 to 2020. You see how the density is vanishing up here in the warming hole region, right? Here, though, it's not. So north of the North Atlantic current, it is light. Okay, so you have that tongue of light fluid, but then it vanishes as it's going in. What's happening is that it takes time for the eddy mixing to erase the density structure. So if you think about it as along the path, this is the path of that flow, and as it's coming here, that density signature is going away, whereas the spice is becoming more and more pronounced. Here, there's no spice, right? Or it's wrong side. But then you come over here, and that's what's happening. So that's what we think is happening in the model, is that the eddy mixing is going on. It's happening later. It's happening out in the middle of the subpolar gyre. The flow that's coming off, though, is lighter. So this is an evolution that happens in space. So, yeah, a little complicated. Yeah.
Paul, is it about this topic? If not, we have one student, and then okay, and then we have other.
Okay.
That thought.
Yeah.
But like, in the end, the fact that the AMOC is weakening is because of the density difference weakening, and that means that the density is changing and it's getting lighter.
Right.
Okay.
That's right. That's this part
Okay.
down here.
And then what you said with the eddies is that if you wait long enough, then you will start getting more cooling, and therefore you're gonna get back to whatever gradient you used to have, and then you're gonna have the AMOC.
That's right. So when you look at, so like for instance, I was asking this question. Let's see, where is that figure that's really useful here? So if you look at this, okay, like this one here, heat flux anomalies. This is here's the SST, right? So there's the warming hole, right? Why is it localized, right? Why is it localized? Why is it out there? Why is it so low? And what is that? Okay, that's warm, right? So you have this tongue of very warm water that's coming in here that cools off, all right? Where it's warm, it's also fresh, right? And so it's light, very light, okay? And that's what's affecting the North Atlantic current, yeah. But as you get out here, it's cooling, so those eddies then are mixing in the cool, and then that's when the blob shows up. So the blob it's taking time for this eddy mixing to happen. It doesn't happen instantaneously.
Thank you so much for your presentation.
Sure.
I know in the early Holocene, like 10,000 years ago,
Yeah.
we have some climate events,
Yeah.
cooling events, and these events was triggered from a mechanism like this, and during like 100, 200 years. So I don't know if you have any idea if it's possible to have this kind of climate event again?
Yes. So, I mean, another question you could ask, which is related, is this related to the glacial cycles, right? Because we have this kind of thing. I think it is. Okay. We haven't looked at this yet, but I think that's exactly right. When you look at, well, let's see, let's go down here. Here. Okay. You notice before, this is the pre-period, so before 1850 or so, down to 1600, so that whole pre-period, you have a stable climate, right? So, but it is fluctuating too, with some long time scales, 50, 100-year time scales. And those two things are going together. So you're seeing that the warming hole gets warmer, and then AMOC is increasing, gets colder, decreases, so they're changing together. If this is, and we haven't really analyzed all this, but we think that, again, if it's related to salinity, you have an excess of fresh water in the subpolar gyre, and then you have more, this, that's going to affect AMOC, it's also going to affect the warming hole. Then you have less, it gets saltier, you have more AMOC, more warming, less warming hole. So that's why we think that both of those things. So yes, I think it's likely this is happening also during this period. But you'd have to go back and I mean, the thing to do is to go back and look, pick apart the components of the density. You know, that will tell you if that's happening. Yeah.
Thank you.
Sure.
Very, very interesting your talk.
Thanks.
If the AMOC changes in secular times and years. So when you talk about weakening, you're talking about weakening in a particular place in the North Atlantic. So if we look at the North Pacific, which is also has a warming of 10 years across many different things, including the energy, so it's weakening in the North Atlantic, but not necessarily in other places. Is it correct?
Yeah. So, I mean, in the North Pacific, are you talking about this also a blob, this warm anomaly that's happening over there?
Yes,
yeah. Yeah. That is a really interesting structure, and I don't understand what is causing that. I mean, I've seen this because it's going on now, and what it looks like is that it propagated eastward from the Kuroshio region across the Pacific, and it's now intensified off the coast here. I don't know what is causing that. I don't think it's this same effect. I think it's something else that's going on. I suspect it's a coupled reaction between the atmosphere and the ocean, so it has to do with some reaction like that. Because the atmosphere is also reacting to that too. That's perturbing the jet stream. So the jet stream is veering north and doing all these things. So yeah, it's related to some of these. But I don't know. I think that's a very interesting topic. There's been some papers about it, but I don't think there's a consensus yet on what that is, what's causing it.
Yes, my point was that this weekend is appearing in the North Atlantic.
Yeah.
But it's a local.
That's right.
Change.
That's right. Yeah.
That possibly that weekend will appear in other places 100 years later or.
Oh, I see what you mean. Yeah, I see what you mean. Yeah, no, okay. It's possible, but what you would need, at least in these cases, you would need that somehow to export that fresh water. What's happening in these cases is that fresh water comes in and it gets stuck in the subpolar gyre, right? So it's stuck north of the Gulf Stream North Atlantic current system, right? And it doesn't get across that. So as long as that continues, and in some of these models, it stays there for 2,500 years. Okay, it stays put. And for it to affect other regions, you'd have to export that fresh water, and that does seem to happen. In some of these later cases, you do tend to see this happen. Yeah.
Anyone else here? Yeah.
Sure.
No, no,
sorry, I don't know how the microphone works. Thank you for your talk as well. I was gonna say, I was wondering how you think that this blob is, because I imagine the blob is not what's weakening the circulation. Like the presence of the blob is not making that the circulation is weakened. I would imagine, because I know that the Arctic is a location of like deep water formation. And is the idea then that this blob is like a way to measure the density differences in the north, or that could be changing the deep water formation?
Yeah. Okay. Actually, I'm glad you mentioned this. Okay.
Thank you.
I didn't make a big deal about this, but the conventional way of thinking about how fresh water affects the overturning circulation is that it floods the convective regions, causes convection to shut down. And then that's what causes the stop in AMOC, right? So it's doing that. That's not what we're seeing. So what we're seeing here, that is happening. So the convective regions are getting shallower, but what we're seeing is that the changes start at lower latitude, start at 40 degrees north. So where is here. So when you look at this, the weakening is happening. It's very localized, right? It's happening right where the North Atlantic current is coming off the coast, or the Gulf Stream North Atlantic current. That current here is weakening first, right? And then you see it spreading. So it spreads back down into the Florida Straits, and it spreads up into the subpolar gyre where the convection is happening. In this model, all the convection happens in the subpolar gyre. It doesn't actually get up to the Nordic Sea. And then as it spreads, now you can see it. It's getting weaker in here, it's getting weaker all here, and that's what AMOC is doing. So AMOC is responding. Again, AMOC, AMOC is only, it's just an integral of the velocity field. So what you're looking at is changes in the velocity field. The changes are happening primarily near that strong current, near the North Atlantic current. That's the main thing that's happening. Yes, the convection is also getting weaker, but it's like the whole thing is shutting down. But it starts for the Gulf Stream. So that's why we think of this more as changing density structure of the ocean. I'll show you one more plot, which I left out. This one. Okay. This one of these plots, and I can't actually tell you which one. I forgot which one is which, but one of them is the actual change in the velocity field. Okay. This is, I think it may be this one. And so there you see the whole current weakening, right? That whole current weakening. This is what happens if you just integrate the density field. So this is the thermal wind relation, which is down here. You integrate that, right? And then you see how much the speed is decreasing. And these two are, of course, identical. Which a lot of oceanographers will say, well, that's no surprise, right? Because the ocean is geostrophic on these scales, and it's hydrostatic. That's all that's going into it. But what we're saying is that, yeah, true. But if you put in a bunch of fresh water, you're changing the density, and then therefore you're changing the velocity field. If you change the velocity field, you change AMOC. Okay? And you don't need to worry about convective capping or anything like that. It's just your change in the velocity. That works.
That's cool.
Thanks.
Yeah, no, thank you. It was good.
Yeah.
Julio? Yeah.
I was surprised by the time series with the AMOC and the salinity.
Yeah. Yeah.
Because, I mean, how do you interpret, like when they go down together, is like it's the melting or the salinity signal. It's actually the time series with the it's the one before where you have suddenly AMOC and salinity go together going down, and then salinity starts to increase, but the AMOC.
Oh, yeah. Okay, the long time scale one. Yeah. Yes. Okay, hold on. There.
Yeah, that one. So the idea is, I mean, it's like, okay, you are at the beginning you are changing the density, but then the thing doesn't recover even though you start increasing the salinity. Is that the?
So what's happening here? Okay, is that so here comes the fresh water, right? So the fresh water is pouring into the system, coming off the coast, and then as it gets out into the center, it's getting cooled. So eddies are tending to make it cooler. All right. So there, bang, you get down here. You have a strong warming hole, you have a weak AMOC, and this other curve, this blue curve is the salinity. So salinity is falling, okay? Now, what happens? The atmosphere now is responding to that cold anomaly, and it starts to warm it up, all right? So and then on the flanks, they're cold, and so it's starting, it's on the flanks, it's warm, and they're starting to cool that down. So the atmosphere is now trying to get rid of these temperature anomalies. It takes a long time. Right? Actually, surprisingly long time. Here it is, 500 years in this model, right, for this to go on. But it's just getting rid of that temperature sink. But again, the salinity, it's hard to get rid of the salinity. Salinity gets into the subpolar gyre. It's really hard to get rid of it, and it stays there. So as long as that salinity is low in the subpolar gyre, then AMOC stays low too. So this is another indication that this is not a causal relation, right? That you can have no warming hole at all and have a very weak AMOC. Right? It's here, it works okay as a proxy. Out here, not at all.
Because the temperature is increasing, so therefore the density should be
Yeah, exactly. Yeah, exactly. Also, the other thing too is that it's localized, right? So it's in that one spot where it's relatively cold. On the sides, it's actually relatively warm. So when you look at the net effect over the subpolar gyre, it's not much. It's salinated, which means it's the big effect. Yeah.
Do we have any other question in here? Yeah, Paulina.
Good.
Thanks.
Okay.
So what I was wondering is, what does the weakening of the AMOC does to the sea ice dynamics? Like, is it going to affect how much ice is melting or not? And so is it basically, does it have a positive feedback or negative feedback?
Great question. That's a great question. There were some studies that have been done, I think 20 years ago or so. There were some studies where they were looking at, so they had, I'm trying to remember the details, but for instance, what you have is you have an atmospheric model, you have an active ice sheet, and then you have something where you can control the heat transport in the ocean. For instance, like with a slab ocean, and then you can just say, here's my heat transport. As you increase or decrease the ocean heat transport, the ice comes up or down, right? So if you turn it down enough, the ice will come all the way down to the north side of the Gulf Stream, right? You have ice. That's the day after tomorrow. That's the day after tomorrow. Right. Okay. What happens here? So that, again, if you think that the ocean changes are happening with timescales of, let's say, AMOC has got timescales here of 20 years, right? Ice is melting in two, right? So there's a big mismatch in the timescale. It's the atmosphere that's doing this. So it is the atmosphere that's responsible. So when you start this, you have this Arctic amplification, right? In these strong climate scenarios. And the whole Arctic is warming up by 4 or 5 degrees, enormous amount. And that's what kills off the sea ice. So in principle, you're right. There could be a feedback between what's happening between the ocean and the ice. But in these scenarios, it's the atmosphere that dominates. Yeah, exactly. But it's a good question. In fact, you need all three. So, they tend to dismiss the ocean. Ocean's super important here. But the atmosphere is absolutely part of this as well. And see, the ice. This is I became a big believer in how important ice is. It's incredible what happens with that.
Okay, so if I may also ask one question.
Yeah.
I wanted to ask, for instance, in here, so you say, I was wondering which 500 years are those? Are those historical years or is it a future run?
This is, now I forget exactly which run this is, but I want to say this is 4 times CO2. So
Okay.
so year 0 here is when you switch on the CO2 levels, and that's when everything goes whoosh, like this. So Arctic amplification, sea ice, everything happens. So, and in 50 years, you see here that AMOC now has reached its minimum. So 50, 60 years is what it takes. So I think this is that. So this is just relative to that increase in CO2 at year 0. And so this really means 500 years since you did that. So 500 years later, there's no more warming hole. It's still fresh, still no AMOC, or weak AMOC.
Okay, because that was my question. I mean, from the previous one of the previous plots, where you have the first historic years, I mean, it's very clear that you have this link between, the AMOC and the North Atlantic warming hole.
Yeah.
And then in here, I mean, it looks like you could have a decoupling, and I guess that's because of the change in the forcing, maybe. So if you have more CO2.
Yeah.
Okay.
So, but this is, like I said, this step function forcing. So this is just where everything is doing that. And then year 0 becomes when that starts. It's a terrible, you wouldn't want to live through that quadruple CO2, but if you're studying it, it's great. I love this scenario because then you see everything happens very abruptly, and you can trace it. So here comes the freshwater down along the boundary. Much harder to do that when you have a realistic scenario because it's more gradual. But here, it's very clear.
Right. And the other one is just a curiosity. So I guess you have heard about the North American warming hole, which is, yes. So I was actually wondering if this name came from that, because that's an atmospheric phenomena that happened in the southeastern US, where you also had a warming hole. And I understand this thing that you say about people getting confused.
The same thing. So I don't know about
It
this.
is the same one, but it's in the atmosphere, and it happened, but that was because of atmospheric forcing from aerosols. So if you have more aerosols there, that's, in contrast with all the global trend, you saw that.
Right.
So, and it's actually the same name. It's North
That's
American warming hole.
Yeah. Same abbreviation.
Yes, exactly.
Yeah, exactly.
Yes. Okay, so, Paco has
May I have a question?
Yeah.
Yeah, I see that considering this scenario of 4 times carbon dioxide concentration is a neat tool. But what about, and then this is essentially warming up the atmosphere, and then everything discloses about from that. But what about taking into account more detailed exchange coefficients? Like you showed the formula for heat, latent heat and surface heat. But those are very, very simplistic exchange coefficients, right? That's for heat. But there are also exchange coefficients for CO2, for momentum, and so on. What could you say about the sensitivity of the results when considering more detailed exchange coefficients?
I think they are sensitive to the details. And I think that's why when you look at this range of models here, you have a range of response. In some cases, you have things which are well compensated. In other cases, you don't, right? So all these parameterizations matter. You know, it's because they're small scale processes, right? You have the heat exchange with the atmosphere. Those are small scale processes. Eddy mixing, which is causing that's all small scale, all parameterized, right? And parameterized, and also sea ice, right? How sea ice melts is parameterized in these models too. I think this is why we see such a huge range of response, why AMOC weakens by 15% in some models and 80% in other models, right? Because there's such a huge range of possibilities. But that said, when you look at these reanalysis of what taking data and so forth, it seems like this is actually happening out there, right? So there is a cold blob that's there that is also fresh, that has very little signature and density, but a strong signature and spikes. So there's indications that from data also that this is going. But we're looking more into this as well, because it's, I think at this point, I mean, I've been working with these sea models now for a couple of years, and now I'm ready for data, real data. So that's what we're going to be doing next, is actually focusing more on real data, trying to look for signatures.
Thank you.
Okay, so we're gonna just very quickly to see if there is any question on Zoom. Please just open up your microphone and your camera if you like. Anyone on Zoom? Okay, so 1 second, because we do have one on YouTube. On YouTube, Cynthia Nava is asking, could this AMOC weakening signal be observed in tropical latitudes? For example, in the SSD and precipitation patterns in the Caribbean Sea?
Okay. So the question is, can this AMOC weakening be seen in SST patterns
in the tropical ocean?
Yeah. Okay. I don't know about that. So let's go back up here. This is, when we look at the changes, let's see here. Okay, yeah, here's what we're seeing. So these are the, so this is, it's not quite what we're after here, but this is change in density due to temperature, change in density due to salinity. Here's the Caribbean down here. And so what you do see is, at least in, again, it's in a model simulation. So, and this varies between models, but in this model simulation, it is getting warmer. Definitely getting warmer in the Caribbean. But at the same time, because it's getting warmer, you have more evaporation. And so it's also getting saltier, right? So, one sign of this would be that you have this kind of change going on. Now, again, just remember, when we look at observations, right, we don't have observations. This is another interesting point. We don't have observations yet that AMOC has weakened. Okay. Now, but we do have observations of a warming hole. Okay. Now, I would just, but we're saying, okay, it looks like at least in these models, these two things go together, right? So you got a warming hole, and AMOC is weakening at the same time. So this is an interesting puzzle that AMOC does not seem to be weakened yet, but there is a warming hole. Why? That we don't know. So this is something we need to look at.
Okay, so thank you so much, Joe. Thank Joe again. Nos vemos afuera para el queso pan y vino. Thank you everyone who joined online.
Yeah.